Most people assume a ship propeller is like a fan. More blades, more push, more speed. That logic feels obvious. It is also wrong, and the real reason is more interesting than the myth. Some propellers really do have 6 or 7 blades. A handful have even more. But walk through almost any major shipping port and look at the stern of a container ship or an oil tanker, and you will see 4 blades, sometimes 5. Not 6, not 8. That is not an accident, and it is not a budget shortcut either. It is the result of naval architects fighting a war on 5 different fronts at once. And blade count is the ceasefire line. A single bronze blade off one of these propellers can weigh more than a fully loaded pickup truck. Picture that. 1 blade. The weight of a Ford F-150 packed with cargo, and a propeller has 3, 4, or 5 of them bolted to a single hub. Before we even talk about how the thing works, understand the stakes. Every blade you add is another truck's worth of metal spinning at 60 to 90 revolutions per minute at the back of the ship. So why add a blade at all? Because of what a blade actually does once it is underwater. A propeller blade is not a paddle. It does not just shove water backward. It is shaped like a twisted airplane wing, and it works almost the same way. As the blade spins, water moves faster over one curved face and slower over the other. That difference in speed creates a difference in pressure. Low pressure pulls, high pressure pushes, and the result is thrust. The same basic principle that lifts a Boeing 737 off a runway, just sideways, and underwater, and against the density of seawater instead of air. More blades means more total surface area biting into the water. In theory, that should mean more thrust every time. And for a while, it does. But here is where the common sense breaks down completely. If a blade spins too fast or is angled too aggressively, the pressure on its back face can drop so low that the water itself stops behaving like water. It vaporizes. Tiny bubbles form right on the metal surface, in the middle of the ocean, with no boiling required. Just pure pressure drop. Those bubbles do not float away peacefully. They get swept into a higher pressure zone a fraction of a second later, and they collapse. Violently, each collapsing bubble slams shut with a tiny localized shockwave, like a microscopic explosion against solid bronze. This is called cavitation, and one bubble is nothing. But a propeller spinning for 18 hours straight across the Pacific generates billions of these collapses. Over months, over years, that bronze surface starts to look like it was blasted with a shotgun, pitted, eaten away, eroded from the inside of the water itself. Adding more blades does not just risk more drag. Done wrong, it can turn a $40 million piece of machinery into scrap metal years ahead of schedule. Now here is something most people never think to ask. If cavitation is this destructive, why does any propeller ever spin fast enough to risk it? The answer is that engineers do not just choose how many blades to use. They choose the exact shape of every single one. And 2 of the most important tools in that shaping process are pitch and skew. Pitch is the angle of the blade. The same idea as the angle on a wood screw or a stairwell. A high-pitch blade bites deep into the water with every rotation, like a screw with widely spaced threads driving fast into soft pine. A low-pitch blade takes a shallower bite, more like a screw with tightly packed threads, slower to advance, but with finer control. Increase the pitch too aggressively on a 4-bladed propeller, and you can squeeze out more thrust per rotation. But push that pitch past a certain point, and you have just recreated the same cavitation problem from a completely different angle. You have made each blade try to grab more water than it can hold on to cleanly, and the back face pressure collapses just like it did with too many blades or too much speed. Skew is a separate fix entirely, and it deals with timing rather than angle. A straight-bladed propeller, the kind you might picture from an old cartoon, slices into the water all at once along its entire edge. That creates a single, sharp pressure pulse with every rotation, the same kind of pulse that risks lining up with a ship's resonant frequency. A skewed blade curves backward like a scimitar, so that instead of the entire edge hitting the water in one instant, the blade enters gradually, tip first, then sweeping inward toward the hub a fraction of a second later. Picture closing a hardcover book by pressing the whole cover flat down at once, a single loud slap, compared to letting the pages fall closed one at a time, page by page, almost silently. A skewed blade smooths that single loud slap into a softer, rolling motion, spreading the pressure pulse out, instead of releasing it all in one violent instant. This is why two propellers can have the exact same number of blades and behave completely differently. A four-bladed propeller with aggressive pitch and no skew can be louder, harsher, and more prone to cavitation than a five-bladed propeller with conservative pitch and heavy skew. Blade count is only one dial on a control panel that has at least 3 other dials right next to it, and naval architects are turning all of them at once. So if more blades risk more damage, why not just go small and simple? 2 blades, maybe 3. Because each blade is also fighting the blade in front of it. As one blade slices through the water, it leaves behind a disturbed, churning wake, a trail of turbulence in its path. The next blade coming around has to cut through that same disturbed water just a fraction of a second later. Think of 4 rowers in a narrow racing scull. One rower alone moves cleanly through still water. Add a second rower, right behind the first, and now their oar is dragging through water, the first rower already churned up. Add a third, a fourth, a fifth, and at some point, every new rower you add is fighting the wake of the rower ahead of them, instead of adding clean new power. Propeller blades do the exact same thing to each other, slicing through water that the previous blade already disturbed. And past a certain blade count, that interference starts eating into the very thrust you were trying to gain. And there is a third front in this war that has nothing to do with water at all. It is about vibration. Every propeller design creates pulses as each blade passes a certain point near the hull. A 2-bladed propeller pulses twice per rotation. A 6-bladed propeller pulses 6 times per rotation. Every ship hull, every engine mount, every steel plate in that vessel has its own natural resonant frequency, the exact vibration rate at which it wants to shake itself apart. Engineers have to make sure the pulse frequency of the propeller never lines up with the resonant frequency of the hull. A wine glass can shatter from a single sustained musical note, not because the note is loud, but because it hits the exact frequency the glass is already vibrating at. A ship hull works the same way. Hit the wrong resonant frequency for thousands of hours across a 25-year service life, and you are not looking at a shattered wine glass. You are looking at fatigue cracks in a steel hull carrying 18,000 containers across the Atlantic. So naval architects are not just optimizing for thrust. They are dodging cavitation, minimizing blade interference, avoiding resonant frequencies, controlling cost, and keeping total weight in check. All at the same time, all with one number, the blade count. And when the engineers at companies like Wärtsilä run those calculations for most large commercial vessels, 4 and 5 blades keep coming out on top. Enough surface area to move 60,000 tons of steel and cargo across an ocean. Not so much that cavitation eats the bronze alive, or vibration cracks the hull, or every added blade becomes another pickup truck's worth of dead weight, fighting the wake of the blade in front of it for almost nothing in return. But 4 and 5 blades is not a single universal rule stamped onto every ship in the world. It is the answer for one category of vessel. The giant tankers and container ships built purely to move cargo efficiently across open ocean for weeks at a time. Walk down the dock to a different kind of ship, and the math changes completely. Take an icebreaker working the Arctic shipping lanes off the coast of Russia or northern Canada. That vessel is not optimized for fuel efficiency over a calm, open crossing. It is optimized to survive slamming into ice sheets thick enough to stop a freight train. Icebreaker propellers are often built with fewer, thicker, almost brutally overbuilt blades, sometimes finished in solid stainless steel instead of bronze, specifically because a thinner, more elegant 4-bladed design optimized for smooth water would crack the first time it clipped a chunk of sea ice the size of a delivery truck. Now go to the opposite extreme and look at a naval vessel, specifically a submarine. Here, the priority is not thrust efficiency or ice resistance, it is silence. A submarine that cavitates loudly is a submarine that can be heard, tracked, and targeted from miles away. So submarine propellers, often called screws in naval terminology, are engineered with extremely high blade counts, sometimes 7 blades or more, combined with extreme skew and incredibly precise manufacturing tolerances, all specifically to keep the pressure on each blade low and even, delaying cavitation until the submarine is moving far faster than it would ever need to during a quiet patrol. The most advanced submarine propeller designs are classified for exactly this reason. The shape of the blade is, in a very real sense, a matter of national security. Then there are smaller specialized vessels, tugboats, for example, hauling enormous container ships into port at walking pace. A tugboat needs maximum torque and pulling power at very low speed, not high-speed cruising efficiency. Many tugboats use what is called a quart nozzle, a circular shroud built around the propeller that changes how the water flows entirely, and the blade count and pitch inside that nozzle are tuned for raw pulling force, closer to the gearing on a tractor than the gearing on a highway car. So, the 4 or 5 blade answer you see on most cargo ships is not the universal answer to propeller design. It is the optimized answer to one very specific problem: moving the maximum amount of cargo, the maximum distance for the minimum fuel cost, without shaking the ship apart or eating the propeller alive. Change the problem, change the ship, and the entire calculation starts over from scratch. 6-bladed propellers do exist. Some specialized vessels need them. Icebreakers pushing through Arctic ice, naval vessels chasing extreme quietness. But for the giant tankers and container ships moving the world's cargo, 4 or 5 blades is not a limitation. It is the answer to 5 different problems that all had to be solved at once. And that cavitation we just talked about, the bubbles collapsing against solid bronze. That same violent, invisible process is also one of the reasons submarines can be heard from miles away, or in the best designs, almost not heard at all. How do you build a propeller blade specifically to stay silent? That is a story about pressure, sound, and some of the most classified engineering in naval history. And it is worth subscribing to find out.